The United States is burning alive. You already know that. But something far more concerning just happened, and almost no one is talking about it. A thermometer in Antarctica just read -105.5 degrees Fahrenheit, the coldest March temperature ever recorded on Earth. That same week, in the same atmosphere, the American Southwest hit 112, 217 degrees of separation, same planet, same week, same sky. Meanwhile, Juneau, Alaska quietly shattered its all-time snowfall record. The Alps got buried under 5 feet of snow in a single 24-hour period. And right now, where that record cold and record heat are colliding across the American Midwest, the atmosphere is releasing all of that tension in the form of destructive tornadoes. That is not weather. That is a system telling you something has broken at a level most people will never think to look at. Tonight, we're going to look. Because 3 rare events happening simultaneously in the stratosphere may have quietly cracked the machinery that keeps this planet livable. Stay with me until the end. What we found here at the Skylab should concern all of us. If this has you hooked, subscribe to the channel, because we are going to keep following this as it develops, and it is developing fast. Drop a comment below, and be honest with me. If the atmosphere just produced a 217-degree temperature spread in a single week, with simultaneous records on both ends of the planet at the same time, what does that actually say about what we have not been paying attention to? I genuinely want to know what you think. Now, let's get into it. Part 1. The week the atmosphere broke. -105.5 degrees Fahrenheit. Let that number sit for a second. Do not move past it. Do not let the brain do what it naturally wants to do with extreme numbers, which is to register them as large and dramatic and then file them away in the category of things that are impressive but abstract. This number is not abstract. It is the temperature recorded at Vostok Station, Antarctica, in March of 2026, the coldest temperature ever measured on Earth in that month, in the entire history of recorded atmospheric observation. Every March that has ever been measured, across every cold location on this planet, across every instrument record that exists, and this is the coldest one. The bottom of the list, the number nothing else has reached in that calendar month in the time that humans have been keeping track. Now hold that number in your mind, because here is the part that should stop you cold, no pun intended, and the part that changes what this story is actually about. That same week, not the same month, not the same season, the same 7-day window, on the same planet, breathing the same atmosphere, the United States shattered its own all-time March heat record at 112 degrees Fahrenheit. 112, the hottest March temperature the country has ever recorded, in the same week that the coldest March temperature the planet has ever recorded was being set on the opposite end of the Earth. 2 records, opposite directions, same atmosphere, same week. That is a 217-degree temperature spread, and I need you to understand what that number actually represents, because it is easy to hear it as dramatic without fully grasping what it means physically. 217 degrees Fahrenheit of separation between the coldest point and the hottest point on Earth in a single week is not just a striking contrast. It is close to the maximum thermal range that Earth's atmosphere is physically capable of producing at the surface under any conditions. We are not approaching some theoretical limit that exists far beyond current experience. We are brushing against the ceiling of what this planet's atmospheric system can generate. We are not talking about 2 different seasons separated by months of transition. We are not talking about 2 different years representing different phases of a climate cycle. We are talking about the same atmospheric system, the same planetary circulation, the same connected envelope of gas that wraps the entire Earth and moves continuously across every surface on it, expressing itself in 2 completely opposite extremes at the exact same moment in time. That does not happen by accident. That does not happen randomly, the product of unrelated weather events coinciding by chance. That is a signal with structure and cause and mechanism behind it. And the question that should be forming in your mind right now is the same one that should be forming in the mind of anyone paying attention. What kind of atmospheric state produces both of those numbers in the same week, and what does it mean that we are living inside one? Because it did not stop at 2 records. While Antarctica was registering temperatures that the month of March had never seen, and the American Southwest was baking under a heat dome that shattered its own historical ceiling, the rest of the atmospheric picture was filling in with data points that, individually, would each constitute a significant weather story. Together, they constitute something else. Juneau, Alaska crossed 201.2 inches of total seasonal snowfall, breaking its all-time record and arriving at roughly 230% of its seasonal average. Not 10% above normal, not 20%, which would already be a year worth remembering, 230%. More than double the expected seasonal total, with enough margin remaining to constitute another full normal season stacked on top of the doubled one. Emergency declarations were filed in a city that thought it understood snow, that had built its infrastructure and its operational assumptions around decades of knowing what its winters looked like. Infrastructure buckled under weight it was never designed to carry because the designers had no reason to design for this. Roofs collapsed. The assumptions embedded in the built environment turned out to be wrong, not because the engineers made errors, but because the atmosphere produced something outside the range that any reasonable historical baseline would have suggested was possible. And in the European Alps, the village of Macugnaga received 1.47 meters of snow, that is just under 5 feet, in a single 24-hour period. Not a season, not a week, 24 hours. Avalanche warnings blanketed a region that is accustomed to significant mountain snowfall and was still overwhelmed by what arrived. Roads closed. The mountains, in the span of a single day, became genuinely impassable in ways that the region's emergency response infrastructure was not equipped to manage, because the accumulation rate was not a larger version of what the region normally experiences. It was a different category of event, produced by a different intensity of atmospheric forcing, arriving through mechanisms that the local geography amplified beyond anything the historical record had prepared anyone to anticipate. Now here is where the timing becomes the entire story, and where the data stops being a collection of separate extreme events and starts revealing its structure. Vostok Station, the Antarctic research post sitting at 3,400 meters of elevation in the most isolated atmospheric environment on Earth, accumulating precise temperature records across decades of continuous measurement, tied its all-time March cold record on one day, and then, the very next day, broke it. The same station, the same instruments, back-to-back days, the atmosphere did not approach a record extreme and then rebound, the way a system experiencing a temporary alignment of favourable conditions typically behaves. It reached the record, held it, and then went further. That is not a spike in the data. A spike looks like a single anomalous point surrounded by more normal values on either side, the signature of a brief intense alignment that the system then moves away from as conditions shift. What 2 consecutive record-breaking days look like is different. That is a system in a state, a sustained, reinforced, self-maintaining state, one that is not oscillating toward and away from the extreme, but is parked in it, pushing further in the same direction rather than correcting back toward baseline. The atmosphere was not passing through minus 105.5 degrees Fahrenheit. It was residing there, and that state, the one producing minus 105.5 in one hemisphere and 112 in another, simultaneously, while burying Alaska in record snow and the Alps in 5 feet of 24-hour accumulation, has a name that researchers have been using to describe what the atmospheric data shows. It is called a thermal fracture. Not a technical term in the formal sense, but a descriptive one that captures something real about what the observational record reveals. A moment where the atmosphere's ability to distribute energy evenly across the planetary surface has broken down so severely that the planet is essentially divided into 2 opposing thermal zones, coexisting in real time, maintained by the same disrupted circulation, each pushing further from normal while the other pushes equally far in the opposite direction. If you're the kind of person who looks at a weather map and reads it in colours, the reds of anomalous warmth and the blues of anomalous cold, the highs and lows of surface pressure, the frontal boundaries where air masses meet, imagine taking that map and pulling it apart at the seams. Not blurring it, not shifting the colours gradually, pulling it apart so that one half is glowing white-hot with anomalous warmth, sitting 6 to 10 degrees Celsius above normal across an extended region, and the other half is buried under anomalous cold sitting 6 to 10 degrees Celsius below normal across an equally extended region. Not a gradient between the two, not a gradual transition zone where temperatures moderate from one extreme toward the other. A line, a fracture, a boundary where the 2 atmospheric regimes are pressed against each other under the weight of weeks of accumulated imbalance. And at that fracture line, right where the air masses are being forced into contact across the American Midwest, something is forming that the atmosphere always produces when pressure builds at a boundary long enough, and the energy on both sides has accumulated far enough. It is forming because the atmosphere does not tolerate sustained imbalance quietly or indefinitely. When the pressure builds long enough, when the energy stored on both sides of a thermal boundary accumulates past the point that the circulation can contain, the atmosphere releases, and that release, when it finally arrives after weeks of accumulation, does not arrive gently or gradually, or in a form that is easy to shelter from. We have seen extreme weather before, cold outbreaks that broke temperature records, heat waves that shattered historical ceilings, snowfall events that overwhelmed cities built for winter, severe weather outbreaks that produced tornadoes in large numbers across the Central Plains. Each of those categories of event has precedent, each has a historical record, each can be placed in a context of prior events that allows researchers and emergency managers and the public to understand what they are dealing with and what range of outcomes is plausible. What the observational record does not have clear precedent for, not at this scale, not in this configuration, not with this degree of simultaneity across multiple continents, and both ends of the thermal spectrum, is all of them at once, all driven by the same underlying mechanism, all expressing themselves within the same brief window of time, all connected not by coincidence, but by the same fractured atmospheric circulation that was holding both the record heat and the record cold in place simultaneously, while producing the conditions for everything else at the boundaries and on the margins. The question that should be sitting with you right now, the one that should feel genuinely unresolved rather than answered by the dramatic nature of the events themselves, is the same one that is sitting unresolved with the scientist working to model what they are looking at. What mechanism, exactly, produces both extremes simultaneously, at this magnitude, with this persistence, across this geographic scale? What part of the atmospheric system broke first to allow this configuration to establish? And the question underneath that question, the one that carries the most weight for everything that comes after this week: how long ago did it break, and what has been building since? Part 2. The temperature dipole. There is a concept in atmospheric science called a dipole, and once you understand it, really understand it, not just the word but the mechanics underneath it, you will never look at a weather map the same way again. The word itself sounds technical and bounded, the kind of term that belongs in a journal paper rather than a conversation about what is actually happening to the planet right now. But the concept it describes is not complicated, and grasping it changes everything about how the events of March 2026 read. A dipole is not two different weather patterns happening in two different places for two different reasons. That framing, two separate events, two separate causes, two separate stories that happen to be occurring simultaneously, is precisely the framing that causes people to miss what is actually going on. A dipole is one pattern, a single coherent atmospheric structure that simultaneously creates opposite conditions at opposite ends of its reach, the way a single bar magnet simultaneously creates a north pole and a south pole, not because two different things are happening at each end, but because one thing is happening across the whole structure at once. Think of it less like two weather systems that happen to be neighbours, and more like a single machine with two outputs. One end of the machine blows hot, the other end blows cold. The machine does not produce heat over here and cold over there as separate processes. It produces both as expressions of the same underlying operation. And in March of 2026, that machine has been running, locked in position, for weeks, with outputs at both ends that have broken records that stood for decades. What we are looking at in March of 2026 is a textbook ridge-trough dipole, amplified to a degree that researchers are genuinely struggling to find historical parallels for, and that difficulty finding parallels is itself a data point worth noting. The western United States is sitting under a persistent atmospheric ridge, a dome of high pressure that forces air to sink, compress, and warm as it descends, the way air in a bicycle pump warms when you compress it. Under a ridge, skies clear because the sinking air inhibits cloud formation. Solar radiation reaches the surface without being intercepted. The ground heats, the air above it heats. And because the ridge is not moving, because it is anchored in place by the dynamics of the amplified jet stream, Rather than being swept eastward in the normal progression of weather systems, the heating accumulates rather than being diluted by the arrival of the next system. Temperatures in the region sitting beneath that ridge have been running 6 to 10 degrees Celsius above normal, not for a day, not for a weekend that produced some warm weather headlines before the pattern shifted, but for an extended period that meteorologists started describing with words like anchored and locked, words that do not appear in normal weather forecasting language, words that signal something beyond the routine variability of a warm spell. Denver, Colorado, sitting at the eastern edge of the ridge's influence, recorded nighttime lows that exceeded the city's average daytime highs for that time of year. Read that again slowly, because it is worth letting land fully. Nighttime lows. The temperatures recorded at the coldest point of the daily cycle, the pre-dawn hours when the surface has had the maximum amount of time to radiate heat away, and temperatures should be at their minimum. Those temperatures were warmer than the average temperature Denver typically experiences at the warmest point of the afternoon in late winter. That is not a warm spell in any ordinary sense of the phrase. That is not the kind of deviation that produces headlines about an unseasonably pleasant week. That is a regime shift in miniature, a brief, localized demonstration of what it looks like when the atmospheric pattern holding a region has moved so far from its seasonal baseline that the normal daily temperature cycle, the familiar rise and fall of warmth through the day, is operating in a range entirely disconnected from what the calendar suggests it should be. The city was, in effect, experiencing a different season than the one the date indicated, and it had been experiencing that different season not for a day or two, but for the duration of the locked pattern. On the other side of the dipole, not another weather system, the other end of the same one, the cold output of the same machine that was blowing hot over the western United States, the pattern flips with a symmetry that is itself scientifically significant. A persistent atmospheric trough, a dip in the jet stream that allows Arctic air to spill southward out of the polar region and pool across the surface beneath it, has been holding temperatures 6 to 10 degrees Celsius below normal across Canada and Alaska for an equally extended stretch. The cold is not a different story from the heat. It is the same story told from the other end of the same atmospheric structure, the inevitable consequence of the same pressure configuration that is producing record warmth on the western side. And here is the specific detail that atmospheric scientists focus on when they look at an anomaly map of this event, the detail that distinguishes an organized atmospheric forcing from a coincidental pattern. The anomalies are nearly symmetrical, equal and opposite, the same magnitude of departure above normal on the warm side as below normal on the cold side, held for the same extended period, covering comparable geographic areas. When you see that kind of symmetry in the atmosphere, it is not coincidence. Symmetrical, equal and opposite anomalies are the signature of a system under organized forcing, something actively maintaining that structure, holding both extremes in place simultaneously with comparable intensity, rather than one extreme being stronger or more persistent than the other, in the way you would expect from two independent weather events that happen to be occurring at the same time. This is where a concept called Rossby wave amplification enters the explanation, and it is worth taking a moment with it because it is the mechanical heart of everything that follows. The reason the dipole locked, the reason it persisted, the reason the anomalies on both sides grew as large as they did and stayed as long as they have. The jet stream, that river of fast-moving air that circles the northern hemisphere at high altitudes and separates Arctic air masses from warmer mid-latitude air, naturally develops waves as it flows. These waves, large-scale undulations in the path of the jet stream, swinging it north and south as it circles the hemisphere, are a normal feature of atmospheric circulation under any conditions. The jet stream always waves. The question that determines whether those waves produce routine weather variability or sustained extreme conditions is how large the waves are and how fast they move. Under normal conditions, Rossby waves are relatively modest in their north-south amplitude, and they propagate eastward at speeds that ensure no single wave pattern dominates any given region long enough to produce a sustained anomaly. A ridge builds, warms a region for several days, and then the wave moves on, and the next system arrives. A trough dips southward, delivers a cold outbreak, and then progresses eastward, and temperatures moderate. The waves are the weather. And because the waves move, the weather changes. When those waves amplify, when the north-south swings of the jet stream become larger, reaching further toward the equator on the cold side and further toward the poles on the warm side, and simultaneously slow down, losing the eastward propagation speed that normally ensures patterns are transient, something changes fundamentally about what the atmosphere is capable of producing. The patterns stop moving. They lock. A ridge that would normally spend 4 or 5 days over a region before progressing eastward instead sits for 2 weeks, 3 weeks, driving temperatures progressively further above normal as the anomaly compounds day after day without the reset that would come from the arrival of the next system. A trough that would normally deliver a cold outbreak and then fill as the flow pattern evolved instead holds position, delivering cold air continuously into the region beneath it, allowing temperatures to sink further below normal with each passing day of uninterrupted Arctic air advection. A locked pattern does not produce one bad week. It produces weeks of compounding extreme conditions on both sides simultaneously, with the magnitude of departure from normal growing as time passes rather than moderating as the system evolves. The persistence is what makes the March 2026 event scientifically unusual, in a way that goes beyond the individual records it has produced. Previous atmospheric dipoles, and there have been others, some of them significant, tended to be shorter lived and weaker. They would establish, hold for several days, perhaps push into a week of anomalous conditions on both sides, and then the jet stream would return towards something closer to a straight, zonal flow as the wave pattern evolved and the blocking structures that had been holding the dipole in place were dismantled by the returning flow. The system would reset, the extremes would moderate, the atmosphere would redistribute the energy that had accumulated on the warm side and allow the cold side to begin recovering towards seasonal norms. The self-correction mechanism would engage before the imbalance grew large enough to pull simultaneous records from both ends of the spectrum in the same week. What we are watching in 2026 has held significantly longer than those historical analogues, with anomalies that have not relaxed between episodes but have instead deepened, the warm side getting warmer and the cold side getting colder as the locked pattern compounds its influence day after day. The atmosphere is behaving less like a self-correcting river finding its way back to its channel after a flood, and more like a rubber band being stretched in both directions at once by forces that are not releasing. And the physics of that metaphor matter more than the metaphor might suggest, because rubber bands under sustained tension do not gently return to rest. They do not gradually relax as the tension continues. They accumulate stress. They store elastic energy in proportion to how far they have been stretched and for how long. And when they release, when the tension finally exceeds what the structure can hold, they do not ease back to their original shape. They snap. They release all of the stored energy at once in a single violent correction. The snap that the current dipole is building toward, at the boundary where the cold side and the warm side are being forced into contact across the American Midwest, is already producing atmospheric conditions that meteorologists describe with a word that in their professional vocabulary carries specific technical weight: explosive. That word is not hyperbole in this context. It is a precise description of what happens when weeks of stored atmospheric energy releases along a narrow boundary in a matter of hours. But before we get to what that release looks like at the surface, we need to understand why the cold side of this dipole just produced something that should have been impossible: a temperature in Antarctica that the month of March has never seen, because Antarctica is supposed to be the most stable atmospheric region on the planet, and something has reached all the way there. Part 3: Antarctica's early descent into winter. Vostok Station sits near the centre of the Antarctic Plateau, approximately 3,400 metres above sea level, in the driest, most isolated atmospheric environment on Earth. There are no cities within 1,000 miles, no highways, no weather stations between it and the horizon in any direction. Just ice, altitude, and silence so complete that the instruments there measure things that most of the planet will never experience and most people will never think to ask about. Vostok holds the all-time planetary cold record, minus 128.6 degrees Fahrenheit, set in 1983, and it has been accumulating temperature data for decades with the kind of quiet, methodical precision that only extreme isolation allows. Researchers there are not easily surprised. The instruments are precise, the records are long, the baseline is well understood. So when Vostok records minus 76.4 degrees Celsius in March, a month that is technically early autumn in the southern hemisphere, and that reading represents a departure of roughly 15 to 20 degrees below what is typical for that time of year, that is not instrumentation error. That is not a calibration artifact. That is the atmosphere doing something it has not done before in the observational record for that month. And the observational record at Vostok is not short. To understand why that number is so strange, you need to understand what Vostok normally looks like in March, because the strangeness is entirely about timing. Typical March temperatures at the station range from around -53 to -60 degrees Celsius. That range reflects the transition between the relative warmth of Antarctic summer, relative being a very generous word for a place that barely climbs above -20 even in January, and the beginning of the long polar night. As the southern hemisphere tilts away from the sun through February and into March, sunlight diminishes, the surface receives less solar input, and temperatures begin to cool. That process is gradual and well characterized. The station has seen it hundreds of times. Temperatures cool as sunlight diminishes and the surface begins radiating heat back into space. That is normal, that is expected. That is autumn on the Antarctic plateau behaving the way autumn on the Antarctic plateau is supposed to behave. What is not expected, what has not been recorded in the station's history for this calendar month, is March temperatures that look like midwinter. Not late autumn, not early winter, midwinter. The kind of cold that usually does not arrive until the polar night is fully established, weeks later, when the sun has completely disappeared below the horizon, and the surface has had additional weeks to shed whatever residual warmth the summer left behind. In March of 2026, that cold arrived early, drastically early, as if the season had skipped a chapter. The mechanism that produces extreme cold at Vostok is called radiational cooling, and it requires a very specific and somewhat unforgiving set of conditions to reach its most extreme expression. It's not simply a matter of being cold to begin with, although that helps. Clear skies are essential. Clouds act as an insulating blanket, trapping outgoing long-wave radiation and preventing the surface from shedding heat efficiently into space. The moment cloud cover develops, the cooling rate slows dramatically. Low atmospheric humidity matters for exactly the same reason, because water vapor itself is a greenhouse gas, and even in the absence of clouds, a moist atmosphere retains outgoing radiation more effectively than a dry one. And then there is the stable temperature inversion, the condition where cold, dense air pools near the surface and remains stratified, unable to mix with the slightly warmer air sitting above it. That inversion is what locks the cooling in place and allows it to compound over time, rather than being diluted by mixing. When those three conditions align simultaneously, clear skies, low humidity, stable inversion, the surface can radiate heat into space at a rate that seems almost aggressive. Temperatures do not just cool, they plunge degree by degree in a feedback loop where the colder the surface gets, the denser the air near the surface becomes, the more stable the inversion becomes, and the more efficiently the cooling continues. It is a system that, under the right conditions, accelerates its own process. The conditions at Vostok in March of 2026 aligned with enough precision and intensity to not only approach record territory, but to reach it, and then to keep going. What makes this event remarkable is not just that those conditions aligned, it is that they aligned with enough sustained intensity to not only set a record, but to tie it one day and then break it the next. Back to back, consecutive days, the atmosphere reached a temperature extreme, held it, and rather than rebounding the way systems typically do after hitting an extreme edge, it went further. That kind of consecutive record breaking is not what you see from a temporary alignment of favourable conditions. A temporary alignment produces a spike, a single anomalous reading surrounded by more normal values on either side. What you see from two consecutive record-breaking days is a system that has entered a state, a sustained, reinforced state, one that kept pushing in the same direction rather than correcting toward baseline. The atmosphere was not passing through an extreme, it was parked in one. And here is where the story becomes more complicated and frankly far more interesting. NASA has documented stratospheric disturbances above Antarctica in 2024, documented, peer-reviewed, published, confirmed by multiple independent analyses. Those disturbances altered circulation patterns in the region in ways that researchers are still working to fully characterize, because the Antarctic stratosphere is not a simple system, and the pathways by which disruptions in that layer influence surface conditions involve processes that take months to propagate and express themselves. There is an open scientific question, genuinely open, not a fringe debate but an active area of research, about whether residual instability from those earlier stratospheric events could be influencing how surface inversions form and intensify in the months that followed. Could the unusual depth of the March 2026 cold event be connected to stratospheric disruptions that began building well before the temperatures at the surface gave any indication of what was coming? Could the inversion that drove the record be stronger or more persistent than normal because the stratospheric environment above it had been altered months earlier? The mechanism is not fully understood. Researchers are careful to say that, and that carefulness is worth respecting. But the timing raises questions that are genuinely difficult to dismiss, and the physical pathways by which stratospheric disruptions influence surface circulation are well enough established in the scientific literature that the hypothesis is not speculative in any irresponsible sense. It is a legitimate open question with supporting physical reasoning. What makes this layer of the story particularly striking is the directionality of it. If stratospheric disturbances above Antarctica in 2024 contributed to conditions that allowed a record-breaking surface inversion to establish in March of 2026, then what we are looking at is not simply an extreme weather event. We are looking at a delayed consequence, a surface expression of atmospheric changes that were set in motion months earlier in a layer of the atmosphere that most people do not think about and cannot observe directly. The surface temperature is the last thing to change. Everything upstream of it, the stratospheric circulation, the inversion structure, the humidity field, the cloud cover, had to align in a specific way over an extended period before the thermometer at Vostok moved to a number it had never reached in March. That is not a weather event in the conventional sense. That is an atmospheric cascade with a very long fuse. What we know for certain is this: Antarctica, the place on Earth most resistant to atmospheric chaos, the region defined by its remoteness and its stability and its sheer physical resistance to the kind of disruptions that affect lower latitudes, just produced a temperature that broke its own record in a month it has never come close to reaching such extremes before. A station that has been measuring temperature for decades, staffed by researchers who are professionally accustomed to extreme cold, recorded something new, something outside the envelope of what that location had previously produced in that calendar month. And the record was not approached gradually over a stretch of unusually cold days. It was tied and then surpassed in back-to-back readings, in a pattern that suggests the system was not oscillating toward and away from extreme conditions, but was instead locked into them, reinforcing them, driving further in a direction rather than correcting back toward normal. And while that was happening, while the cold end of the planet was doing something it had never done before in March, the northern end of the same atmospheric system was doing something equally extraordinary on the opposite end of the thermal spectrum. The two events are not coincidental. They are connected, and the connection does not run along the surface, where you could trace it on a map. It runs through the stratosphere 30 kilometers above the surface, through a layer of atmosphere that most people have never thought about, and that scientists are only now beginning to fully understand as a driver of the weather we experience at the ground. The question is what connects them. The answer starts about 30 kilometers above your head, and it is stranger than you might expect. Part 4. The collision has already started. There is a line running across the central United States right now, and it is not on any political map. It does not follow a state border or a river or a ridge of terrain. It is invisible from the ground, and it moves slowly, the way a fault line shifts, not enough to see, but enough to feel when it finally gives. It is the boundary between the heat side and the cold side of the dipole we have been tracking, the edge where 217 degrees of temperature spread compresses into a zone of atmospheric violence that meteorologists assign numbers to on a scale of 1 to 5. The region received a Level 3 Enhanced Risk designation from the Storm Prediction Center. That is the third highest category on their scale, sitting above slight and enhanced and below only moderate and high. It does not get issued casually. It does not get issued for garden variety spring storms. It gets issued when the atmosphere has built enough organised energy and enough of the right configurations that forecasters can say, with confidence, that significant and potentially violent weather is not just possible but expected. Level 3 is the forecast office telling you, this is serious, and you should act accordingly. To understand why this particular setup is so dangerous, why this boundary in this week, with this specific combination of air masses, warranted that designation, you need to understand what happens when a heat ridge does not just warm the surface, but exports its instability eastward. The heat dome sitting over the American Southwest has been doing more than raising temperatures. It has been manufacturing and transporting a very specific atmospheric ingredient that sets the stage for the most violent storm structures the Central Plains can produce. That ingredient has a name: the elevated mixed layer. It is a mass of hot, dry air that originates over the elevated terrain of the Southwest, the high desert plateaus of Arizona, New Mexico, and Colorado, where the surface heats the overlying air to extreme temperatures before that air gets lofted eastward at altitude by the prevailing flow. It travels at height, above the surface, and when it arrives over the Central Plains, it does something that seems counterintuitive at first, but is mechanically critical. It acts as a lid. Below that elevated layer of hot, dry air, something very different is happening at the surface. Warm, moist air is flowing northward from the Gulf of Mexico, drawn in by the pressure gradient ahead of the approaching storm system. This air is laden with moisture, unstable, and desperately wanting to rise. In a normal situation it would. Convection would initiate, clouds would form, storms would develop, and the energy would release in a distributed, relatively gradual way across a broad area. But the elevated mixed layer sitting above it prevents that from happening. The hot dry air aloft is denser than the moist air below wants to become as it rises, and it suppresses that rise, capping it, containing it, forcing the energy to stay near the surface and accumulate rather than release. The atmosphere builds energy the way a pressure cooker builds steam, contained, accumulating, waiting. Meteorologists call this the cap, and a strong cap on a day with high atmospheric instability is one of the most consequential forecast elements in severe weather meteorology, because it determines not whether the energy releases but when and how violently it does so. When the cap breaks, when the lid finally gives, either because the surface heating becomes strong enough to punch through it, or because a forcing mechanism like a front or a dry line provides the trigger, the energy that has been building underneath does not release gradually. It does not leak out in a distributed, manageable way across the afternoon. It releases all at once, in organized convective explosions that meteorologists call discrete supercells, individual rotating thunderstorms that can reach 40 to 60,000 feet into the atmosphere, that can maintain their structure and their violence for hours, and that can travel hundreds of miles while producing continuous hazards along their entire path. Supercell thunderstorms are the atmosphere's most efficient mechanism for releasing large amounts of instability quickly. They are also among the most dangerous weather phenomena on Earth, capable of producing hail the size of baseballs, straight-line winds that exceed hurricane force, and tornadoes, sometimes large, long-track tornadoes, that can remain on the ground for miles. This is not a standard storm system moving through the region on a typical spring afternoon. This is the atmosphere behaving like a pressure release valve, the dipole's two sides, having built an imbalance over weeks of pattern locking, finally forced into contact along a narrow boundary and releasing the stored energy in the most efficient and most violent way the atmosphere knows how. The warm, moist air from the Gulf of Mexico wants to rise. The cold, dense air pressing southward from Canada wants to sink and undercut everything ahead of it. Where those two air masses meet along the boundary, the atmosphere creates rotation, horizontal spin generated by the contrast between the warm surface flow and the cold elevated flow, tilted into the vertical by the convective updrafts of developing thunderstorms. That rotation, given sufficient wind shear, a change in wind speed and direction with altitude that the jet stream is currently providing in abundance, organizes into the structured, persistent rotation of a supercell. And supercell thunderstorms in this environment, with this much instability and this much shear available, do not just produce heavy rain and isolated wind damage. They produce large hail, widespread damaging straight-line winds, and tornadoes, multiple tornadoes, potentially violent long-track tornadoes of the kind that appear in the historical record with damage paths measured in miles and widths measured in hundreds of yards. What makes this particular outbreak especially hazardous is an element that does not always receive the attention it deserves in public storm coverage, an element that has nothing to do with the meteorology itself and everything to do with the humans in the path of it: timing. The most intense convective activity for this event was forecast to peak after dark. Not during the late afternoon heating hours when cap breaking is most common and when most people are awake, aware, and able to respond. After dark. Nocturnal tornado outbreaks are significantly and measurably more dangerous than daytime outbreaks of comparable meteorological intensity, and the reasons are entirely human. People are asleep, phones running warning alerts may not wake everyone, visibility is zero, a tornado at 2 in the afternoon is sometimes visible at a distance, giving people precious additional seconds to act. A tornado at 2 in the morning is invisible until it is on top of you. Warning, lead times that feel manageable in daylight feel impossibly short in darkness, when the time between receiving a warning and reaching shelter can be consumed entirely by the seconds it takes to wake up and understand what's happening. The same tornado, with the same damage potential, striking the same neighbourhood, causes more casualties at night than it does during the day. That is not speculation. That is what the historical fatality data consistently shows, and this event was forecast to deliver its worst hours in darkness. Behind the storms, following them with the kind of immediacy that leaves no recovery time, comes what forecasters were calling the pneumonia front, the cold air mass advancing behind the storm system with a speed and intensity that reflects just how much pressure has built on the cold side of the dipole. Temperatures were expected to drop 30 to 40 degrees Fahrenheit within hours of the storm's passing, not over a day, not gradually through the following morning, within hours. The violence of the atmosphere's correction is always proportional to the magnitude of the imbalance it is correcting, and the imbalance here has been building for weeks. Weeks of locked dipole, weeks of pattern reinforcement, 217 degrees of thermal spread compressed into a single planetary system. When that system finally begins equalizing, when the pressure release valve finally opens, it does not do so quietly, or gently or gradually. It does so all at once along a line with everything the atmosphere has stored on both sides of that line, arriving at the boundary simultaneously. The Midwest is the collision point. It is where the experiment ends and the consequences begin. It is where weeks of atmospheric imbalance accumulated through a cascade of events most people never heard about and cannot see, finally arrives at the surface in a form that is impossible to ignore, and the fracture in the jet stream that created this entire situation, that allowed the dipole to lock, that kept the heat side hot and the cold side cold for weeks, that compressed 217 degrees of temperature spread into a single atmospheric system. That fracture did not start at the surface. It did not start in the troposphere where storms form and weather happens and we live our lives. It started 30 kilometers above all of it, in a layer of the atmosphere most people have never heard of, driven by events that began months ago and have been propagating downward ever since. The surface is the last place the signal arrives, and it has just arrived. Part 5. The Triple Stratospheric Warming Event. Most people, when they think about weather, think about the layer of the atmosphere they can see, the clouds, the storms, the wind at their face, the sky that changes colour at sunrise and goes dark at night. That layer has a name, the troposphere. It extends roughly 12 kilometers above the surface, and it is where essentially everything we experience as weather originates and resolves. Rain forms there. Thunderstorms grow and collapse there. The jet stream flows through its upper reaches, fronts advance and retreat across its lower levels. For practical purposes, for most of human history, the troposphere was weather, and everything above it was simply not. Above the troposphere sits the stratosphere, extending upward to about 50 kilometers, and for most of recorded history it was treated as a kind of atmospheric attic, cold, thin, calm, largely irrelevant to anything happening below. Scientists knew it existed. They sent balloons into it. They measured its temperatures and its chemistry. But the idea that events occurring 30 to 50 kilometers above the surface could meaningfully influence the storms and temperatures that people experienced at the ground was not a mainstream scientific position for most of the 20th century. It was considered at best a marginal effect. At worst, it was dismissed entirely. That assumption turned out to be wrong, not slightly wrong, not wrong in ways that required fine-tuning and adjustment. Wrong in a way that, once the evidence accumulated sufficiently and the mechanisms were understood well enough, changed how atmospheric scientists think about the relationship between the upper atmosphere and the surface weather that affects billions of people. And it changes how we think about everything that has happened in March of 2026, because the events that drove the records, the dipole, the outbreak, and the simultaneous extremes did not begin at the surface. They began 30 kilometers above it. What is called a sudden stratospheric warming event is exactly what it sounds like, and at the same time its consequences are nothing like what the name alone implies. The name suggests a temperature anomaly in a remote layer of the atmosphere, interesting to researchers, irrelevant to anyone else. The reality is considerably more consequential. In a sudden stratospheric warming, temperatures in the stratosphere near the polar region can rise by 30 to 40 degrees Celsius in a matter of days. To put that in context, that is a larger temperature swing than most mid-latitude cities experience between their coldest winter day and their warmest summer day, compressed into 72 to 96 hours, occurring in a layer of atmosphere that most people will spend their entire lives never thinking about. The warming itself is dramatic, but the warming is not the point. The warming is the symptom of something structural happening to the circulation above the pole. The polar vortex is the structure in question. It is a large, organised circulation of cold air that sits in the stratosphere above the Arctic during the winter months, spinning counterclockwise, containing the coldest Arctic air within its boundaries, the way a spinning top contains its centre of gravity. Under normal conditions, the polar vortex is strong, coherent and effective at its job. Cold air stays in the polar region. The stratospheric circulation remains organised. And because the stratosphere and the troposphere are coupled, because they communicate, because changes in one propagate into the other over time, a strong, stable polar vortex tends to support a stronger, more organised jet stream in the troposphere below it. The containment works at both levels simultaneously. When the polar vortex is healthy, the weather downstream tends to be more orderly. Not benign, weather is never entirely benign, but more predictable, more seasonal, less given to the kind of extreme and persistent pattern anomalies that produce simultaneous records at opposite ends of the thermal spectrum. When a sudden stratospheric warming event disrupts the polar vortex, that containment begins to fail. The vortex weakens, losing the organised spin that keeps Arctic air corralled above the pole. In moderate events, it distorts, elongating, shifting off-centre, allowing some Arctic air to begin migrating equatorward, while the vortex attempts to recover. In the most extreme events, it does not distort, it splits. The single coherent circulation breaks into multiple separate lobes, each carrying a fraction of the original vortex's cold air, each now free to influence the circulation at lower latitudes in ways that a single contained vortex never would. When that happens, the containment system for Arctic air does not just weaken, it fails structurally. And the effects of that structural failure do not arrive at the surface immediately. There is a delay, typically 1 to 3 weeks, as the disruption propagates downward through the atmospheric layers, reshaping the pressure patterns and wind fields in the upper troposphere before finally expressing itself in the surface weather that people can feel and measure and shelter from. This season, Earth experienced 3 of them, 3 sudden stratospheric warming events in a single winter season. That number requires emphasis because it is easy to hear and not fully register what it means. 3. In one season. Multi-event winters of this kind occur roughly once per decade in the observational record, and even in those rare seasons, the events typically vary enough in intensity and are spaced far enough apart that some degree of atmospheric recovery can occur between disruptions. The vortex weakens, the surface pattern shifts, and then, before the next event arrives, the system has time to begin reassembling some version of its prior structure. The disruptions are serious but sequential. The atmosphere gets hit, staggers, and starts to recover before the next blow lands. What happened in 2025 into 2026 was different in a way that matters enormously to everything that followed. The events stacked. January brought the first disruption, a significant sudden stratospheric warming that weakened the polar vortex and began pushing energy downward into the troposphere. February brought the second, arriving before the atmosphere had completed its recovery from the first, adding a new layer of stratospheric disruption onto a system that was already operating in a destabilized state. And March brought the third, the most structurally significant of the 3, with documented zonal wind reversals at 60 degrees north latitude and 10 hectopascals of pressure. which is the standard reference level where researchers measure stratospheric circulation and assess vortex behaviour. At that level, the winds did not just slow, they reversed. Westerly flow, the normal direction of stratospheric circulation around the pole, gave way to easterly flow, a signature of a vortex that has not merely weakened but has been fundamentally disrupted at its core. And the polar vortex under that forcing did not just weaken further, it split into multiple lobes, a structural breakdown rather than a simple reduction in intensity. Multiple fragments of what had been a single coherent circulation, now displaced, now influencing the tropospheric flow below them in complex and compounding ways. NASA characterized this season as involving a series of rare disturbances. That language deserves a moment of attention, because in the carefully measured and deliberately conservative vocabulary of institutional science, the phrase series of rare disturbances carries significant weight. These are not researchers given to dramatic framing. These are people whose professional culture rewards precision and penalizes overstatement. When that culture produces language like series of rare disturbances to describe a sequence of atmospheric events, it is the equivalent of a very composed person saying, in a very level voice, that something unusual is happening and that it warrants serious attention. It is, in the understated language of institutional science, about as alarmed as it gets. Because what 3 stacked sudden stratospheric warming events means in practice is not simply 3 anomalous weeks in the stratosphere that researchers will write papers about. It means the polar vortex, the containment system that keeps Arctic air from spilling into the mid-latitudes, that supports the jet stream, that maintains the organised circulation patterns that allow seasonal weather to behave seasonally, failed. Not once, not twice. 3 times in succession, each failure arriving before recovery from the previous one was complete, each disruption propagating downward into a troposphere that was still absorbing the consequences of the disruption before it. Each event pushed energy downward. Each pushed it into a system that had less resilience to absorb it than it would have had if the events had been spaced further apart. And the cumulative result of that compounding weeks of stratospheric disruption, layering onto weeks of prior disruption, all of it propagating downward through the atmospheric column, is what we see expressed at the surface in March of 2026. Record cold at Vostok. Record heat in the American Southwest. A pattern-locked dipole holding both extremes simultaneously for weeks, and a severe weather outbreak forming at the boundary where the 2 sides of that dipole are finally being forced into contact. The surface is not generating these extremes independently. It is receiving them, the delayed, compounded, surface-level expression of a stratospheric cascade that began in January and has been propagating downward ever since. Which forces a question that the observational record does not yet have a confident answer to, but that atmospheric scientists are asking with increasing urgency. If 3 stacked sudden stratospheric warming events can produce this level of surface disruption, can fracture the jet stream, lock the dipole, and pull simultaneous records from both ends of the thermal spectrum in the same week, what happens if this becomes more common? What happens if the stacking is not an anomaly but a pattern? And the part of that question that should stay with you, is it already? Part 6. The jet stream is no longer a river. Think of the jet stream under normal conditions as a river. Not a slow, meandering river winding through flat terrain, but a fast, purposeful one, the kind that moves with enough force and direction that everything in it gets carried along whether it wants to or not. Fast-moving, relatively straight, flowing from west to east around the upper latitudes of the northern hemisphere at speeds that can exceed 200 miles per hour at its core. It separates Arctic air to the north from warmer mid-latitude air to the south, and because it moves quickly and maintains a relatively straight course, it sweeps weather systems through with it like a conveyor belt that never stops. Storms form along its southern edge, travel with it, and exit to the east before they can build into anything sustained or extreme. No pattern stays long enough to become truly anomalous. Cold snaps last days, not weeks. Heat waves build and then get swept away as the next system comes through. The river moves and takes its contents with it, and the result, imperfect, variable, occasionally dramatic, is something close to atmospheric equilibrium. Energy moves, patterns shift. The extremes that do occur are bounded by the simple fact that the circulation does not allow them to stay in one place long enough to compound. Now think about what happens when that river slows down and starts to meander. Not stops, it never stops entirely, but slows significantly, losing the forward momentum that kept its path relatively straight and its contents moving. When a river slows, the curves get bigger. The water, no longer moving with enough energy to maintain a straight channel, starts to swing laterally, looping north, then south, then north again, in curves that grow wider and more exaggerated the slower the flow becomes. The water moves more slowly through those curves, and in the tightest bends, where the curve doubles back on itself most severely, some sections of the river almost stop moving entirely. They become stagnant loops, water that is technically still part of the river but is no longer going anywhere, circulating slowly within its own curve while the main flow passes around it. In atmospheric terms, that is precisely what a highly amplified meridional jet stream looks like, and the analogy is not casual, it is mechanically accurate in the ways that matter. Instead of flowing relatively straight from west to east, what meteorologists call zonal flow, the jet stream develops large north-south waves, swinging far down into lower latitudes in some places and retreating far poleward in others. The technical term for these waves is Rossby waves, named after the meteorologist Carl Gustav Rossby, who first described their behaviour in the 1930s, and they are a normal feature of the jet stream under any conditions. The jet always waves. The question is how large those waves are, how fast they move, and whether they stay in one place long enough to matter. Under normal zonal conditions, Rossby waves are relatively small, and they propagate eastward quickly enough that no single wave pattern dominates any given region for an extended period. Under amplified meridional conditions, those waves grow larger, slow down, and in some cases become stationary, locked in place by the dynamics of the flow itself, neither growing nor dissipating nor moving on. Where the jet stream dips south in one of those amplified waves, it drags Arctic air with it, pulling cold air from the polar region down into the mid-latitudes well south of where it would normally reach. Where it bulges north in the opposing part of the wave, it allows warm subtropical air to surge poleward, carrying heat into regions that would ordinarily be insulated from it by the jet stream's position. The result, when those waves are large enough and slow enough, is exactly the kind of thermal structure we have been tracking throughout this discussion. Persistent anomalous warmth on one side, persistent anomalous cold on the other, both sustained by the same wave pattern, both expressions of the same degraded atmospheric circulation. This is not a theoretical description of how the jet stream could behave under certain conditions. This is what the observational record shows for the winter and spring of 2025 into 2026. The jet stream has been operating in a highly meridional state for an extended period, with amplified waves that have been persistent rather than transient, holding their positions for weeks rather than the days that would be typical of a more energetic zonal flow regime. And embedded within that meridional pattern, reinforcing it and being reinforced by it, are structures called blocking highs, regions of high pressure that develop in the ridges of the amplified jet stream waves and then resist the normal eastward progression that should eventually dismantle them. Blocking highs are, in a sense, the atmosphere's version of a traffic jam. Under normal conditions, high pressure systems form, influence the weather beneath them for a period, and then get swept eastward by the jet stream flow before they can establish a prolonged influence on any one region. But when the jet stream is sufficiently amplified and slow, a high-pressure system can become embedded in the wave pattern in a way that the flow cannot easily dislodge. The blocking high persists. Days pass, then a week, then two. The weather pattern beneath it does not evolve, it simply continues, deepening its influence on surface temperatures, soil moisture, vegetation stress, and all the other surface conditions that respond to sustained atmospheric forcing. On the warm side of the dipole we have been tracking, a blocking high anchors the heat ridge over the western United States, holding temperatures 6 to 10 degrees Celsius above normal for weeks. On the cold side, a stalled trough anchors the cold pool over Canada and Alaska, holding temperatures equally far below normal for an equally extended period. And the jet stream, rather than sweeping either of these structures away and restoring something closer to normal circulation, flows around them, its amplified waves curving around the blocking patterns, reinforcing their positions rather than eroding them. There is an active and genuinely contested scientific debate about why blocking events and meridional jet stream behaviour appear to be occurring more frequently. and it is worth being honest about the state of that debate rather than presenting a cleaner narrative than the evidence currently supports. The leading hypothesis involves a process called Arctic amplification, the well-documented and scientifically robust observation that the Arctic region is warming roughly 2 to 4 times faster than the global average. The mechanism behind Arctic amplification involves several reinforcing feedbacks, the most significant of which is the loss of sea ice. Sea ice is highly reflective, bouncing a large fraction of incoming solar radiation back into space. As sea ice retreats, darker ocean water is exposed, absorbing more solar energy, warming further, melting more ice, and so on in a self-reinforcing cycle that has driven Arctic warming at a pace that has consistently exceeded the projections of earlier climate models. As the Arctic warms relative to the mid-latitudes, the temperature difference between the polar region and the temperate zones decreases, and that temperature difference, that gradient, is what powers the jet stream. The jet stream exists because of the contrast between cold polar air and warm subtropical air, pressing against each other along the boundary between them. A large contrast produces a strong, fast jet. A smaller contrast produces a weaker, slower jet. And a weaker, slower jet, as we have established, is more susceptible to the kind of large amplitude, slow-moving wave patterns that allow weather to become geographically locked. The hypothesis is physically coherent, mechanically plausible, and supported by the directional trend in the observational data. The Arctic is warming, the gradient is decreasing, the jet stream by the physics of the mechanism should be weakening, and the surface weather patterns we are observing are consistent with what a weakening, more meridional jet stream would produce. The counter-arguments exist, and they deserve acknowledgement rather than dismissal. Some researchers argue that the statistical evidence for increased jet stream waviness and blocking frequency is not yet robust enough to draw firm conclusions, that the observational record for these phenomena is too short, too noisy, and too susceptible to natural variability to confidently separate a genuine trend from an unusually active period within a range of normal behaviour. That debate is ongoing in the peer-reviewed literature, genuinely unresolved, and anyone who tells you it is settled in either direction is overstating what the evidence currently supports. Science is still working on this one, honestly and actively working on it. What is not debated is the consequence of what we are observing right now, regardless of its cause. A slow, amplified jet stream means heat becomes geographically locked on the warm side, and cold becomes geographically locked on the cold side. It means that whatever pattern establishes under those conditions does not move on in 3 days. It stays for weeks, deepening its influence, compounding its effects, driving surface conditions progressively further from normal on both ends simultaneously. It means the boundary between those locked regions becomes a zone of violent atmospheric negotiation, where the energy that has been building on both sides for weeks finally has to go somewhere. The atmosphere is not broken in the sense of having stopped functioning. It is still doing its job, still trying to redistribute energy from the equator toward the poles, still generating the circulation patterns that make that redistribution possible. But it is doing that job in a degraded state through a circulation that is slower and more distorted than it should be. And a degraded circulation does not produce moderate weather. It produces the 217-degree spread. It produces simultaneous records at both ends of the thermal spectrum. It produces the Midwest outbreak forming at the collision boundary. The mechanism is the stratospheric disruption that fractured the vortex. The effect is the locked, amplified jet stream that followed. And the surface response, everything we have been tracking, everything that broke records this week, is the delayed, compounded, inevitable consequence of a cascade that started 30 kilometers above all of us, weeks ago, in a layer of the atmosphere that most people still believe has nothing to do with the weather outside their window. Part 7. Downward propagation and the invisible delay. Here is a detail that changes how you read everything that happened in March of 2026, and it is the kind of detail that, once you understand it, makes the entire sequence of events feel less like a collection of separate weather anomalies, and more like what it actually is: a single, coherent story unfolding across time in a system far larger and more interconnected than the daily weather forecast suggests. The sudden stratospheric warming events that disrupted the polar vortex this season did not cause immediate surface effects. They never do. That is not a limitation of the events themselves, it is a fundamental feature of how the stratosphere and the troposphere communicate with each other, and understanding that communication is essential to understanding why March of 2026 looks the way it does. The mechanism by which a stratospheric disruption reshapes surface weather involves a process called downward propagation, and it operates on a timescale of 1 to 3 weeks. That timescale is not an approximation or a rough estimate. It is a well-characterized feature of stratosphere-troposphere coupling that has been documented across decades of observational data and replicated in atmospheric models with enough consistency to be treated as a reliable feature of how the system behaves. What it means in practice is that by the time the surface is responding to a stratospheric event, by the time the blocked jet stream and the locked dipole and the record temperature anomalies are expressing themselves at the level where people live and breathe and measure temperature, the stratospheric event that set all of it in motion is already weeks in the past. The cause and the effect are separated by enough time that the connection between them is not obvious from the surface. You have to know to look upstream. You have to know that the atmosphere has a memory, and that what it is doing today reflects decisions, in a manner of speaking, that were made in a different layer of itself weeks ago. The physics of downward propagation work roughly as follows. When the polar vortex weakens or splits in the stratosphere, the change in its circulation alters the pressure patterns and wind fields throughout that layer. The stratosphere is not a sealed compartment. It exchanges energy and momentum with the troposphere below it through a variety of mechanisms, including wave activity that propagates across the boundary between the two layers. As the altered stratospheric patterns begin influencing the flow at the top of the troposphere, that influence works its way progressively downward, from the upper troposphere, where the jet stream cores reside, into the mid-troposphere, where the large-scale pressure patterns that steer surface weather systems are determined, and finally into the lower troposphere and the surface circulation, where the temperature anomalies and wind patterns and storm tracks that constitute what we call weather become observable and measurable. At each level of that downward progression, the signal becomes more diffuse and more complex. It gets mixed with other processes already occurring at that level. It interacts with surface boundary conditions, the distribution of land and ocean, the temperature of the sea surface, the position of mountain ranges that deflect airflow. By the time it reaches the surface, it does not look like a clean stratospheric signal anymore. It does not arrive wearing a label that says this came from the polar vortex 6 weeks ago. It looks like a blocked jet stream, a persistent dipole, a locked pattern of extreme conditions on both sides of a temperature boundary. It looks from the surface like weather, complicated, variable, hard to predict weather that seems to be behaving strangely without any obvious reason why. What downward propagation means for the specific timeline of 2025 into 2026 is clarifying in a way that is uncomfortable once you follow it through. The January sudden stratospheric warming event, the first of the three, began propagating its signal downward through the atmospheric layers in the weeks following the disruption. By February, that signal was expressing itself in the tropospheric circulation, beginning to influence the position and behavior of the jet stream, beginning to favor the kind of blocked meridional flow that allows patterns to persist rather than progress. The troposphere in February was already operating under the influence of a stratospheric disruption that had occurred weeks earlier, its circulation subtly but measurably altered from what it would have been in the absence of that disruption. And then, before that February circulation had completed its response to the January event, before the system had had time to absorb the stratospheric forcing and return towards something closer to its baseline state, the February sudden stratospheric warming event arrived. The second disruption landed on top of a troposphere that was already responding to the first one. The new stratospheric signal did not replace the old one, it added to it, compounded it. The troposphere, already tilted away from its normal circulation by the January forcing, received an additional push in the same destabilizing direction before it had recovered from the first push. The two signals layered onto each other in the tropospheric circulation, reinforcing the blocked meridional pattern that the first event had begun to establish. February surface weather reflected this layering, patterns persisting longer than they should have, anomalies on both the warm side and the cold side of the circulation holding with unusual tenacity, the jet stream maintaining its amplified, meandering character rather than relaxing back toward the straighter, faster flow that would have allowed patterns to move and extremes to moderate. And then March arrived, and with it the third event. the one with the documented zonal wind reversals at 60 degrees north and 10 hectopascals, the one where the polar vortex did not merely weaken, but split structurally into multiple lobes. That event, the most mechanically significant of the three, arrived on top of a troposphere that had already been destabilized by two prior disruptions, without adequate recovery time between any of them. The atmospheric system that received the March stratospheric forcing was not a system at baseline, absorbing a disruption from a position of equilibrium and resilience. It was a system already operating under sustained stress, already expressing the compounded consequences of two prior events, already locked into circulation patterns that reduced its ability to respond to new forcing in a self-correcting way. The March event did not have to work as hard to produce its effects as it would have in isolation, because the work of destabilization had already been partially done by what came before it. It pushed a system that was already leaning. The surface extremes we are observing in March of 2026 are therefore not the product of one stratospheric event, or even of three separate events each contributing its own distinct surface signal. They are the layered, compounding, mutually reinforcing consequence of three disruptions arriving in sequence faster than the system could absorb and recover from each one, a cascade in the precise technical sense of the word, where each stage of the process alters the conditions for the stage that follows, amplifying the overall outcome beyond what any single component would have produced independently. This is why researchers use the word cascade when they describe the season, not because the events are connected in a simple linear chain where A causes B causes C in a clean, traceable sequence, but because each disruption added its forcing to an atmospheric state that was already stressed by prior disruptions, progressively reducing the system's capacity to recover to baseline, progressively increasing the magnitude of the surface response that the compounded forcing would eventually produce. The current surface patterns, the locked dipole, the amplified meridional jet stream, the record temperature anomalies on both ends of the thermal spectrum, the severe weather outbreak at the collision boundary, represent weeks of accumulated stratospheric forcing that the troposphere has been absorbing and expressing in slow motion, layer by layer, level by level, as the downward propagation of three stacked disruptions has worked its way through the atmospheric column. And here is the part that should stay with you, the part that makes the cascade framing more than just a retrospective description of what already happened. The pattern is not necessarily over. The surface may still be responding to forcing that has not yet fully propagated to the levels where we measure and experience it. The troposphere does not finish processing a stratospheric disruption on a fixed schedule. The 1 to 3 week propagation timescale is an average, a central tendency, not a hard cutoff, after which the stratospheric influence ceases and the surface returns to independence. The signal can linger. It can interact with surface boundary conditions in ways that extend its influence beyond the typical propagation window. The locked patterns we are observing may persist not because new stratospheric forcing is continuously arriving, but because the troposphere, having been pushed far enough from its baseline circulation, has entered a state that is self-reinforcing, a state that the atmosphere maintains not because it is still being driven, but because the dynamics of the pattern itself resist the return to equilibrium. What comes next is therefore not simply a question of whether another stratospheric event will arrive to add a fourth layer of disruption to what is already an unusually stressed system. It is a question of whether the system has enough internal resilience, enough of the self-correcting capacity that normally returns weather patterns towards something seasonally appropriate, left to begin recovering on its own. The forcing from 3 stacked sudden stratospheric warming events has been applied. The cascade has run. The surface is expressing the consequences, and what we do not yet know, what the models cannot yet tell us with confidence, is whether the atmosphere has been pushed far enough from its normal operating state that recovery will be slow, partial, and punctuated by continued extremes, or whether the pattern will eventually break, the jet stream will eventually relax, and the dipole will eventually dissolve back into something that resembles a normal spring. What we know is that the resilience required for that recovery has been spent, event by event, since January. The question of whether enough remains is one the atmosphere is currently in the process of answering, and the surface, as always, will be the last place we see the result. Part 8. Why the system locked instead of resetting. Under normal atmospheric conditions, a sudden stratospheric warming event produces a period of disrupted surface weather lasting roughly 2 to 4 weeks. after which the jet stream gradually returns toward a more zonal, less amplified state. The timeline is well characterized. The disruption arrives in the stratosphere. The signal propagates downward over 1 to 3 weeks. The surface responds with blocked patterns, displaced air masses, and temperature anomalies that can be significant and prolonged, but that are ultimately bounded by the atmosphere's internal tendency to restore itself. Then, as the stratospheric forcing dissipates and the polar vortex begins to recover, the tropospheric circulation starts relaxing back towards something closer to its seasonal baseline. The system resets. Patterns that were locked begin to move again, carried eastward by the returning zonal flow. Extremes that had accumulated on both the warm side and the cold side begin to moderate as energy redistribution resumes. The atmosphere's internal dynamics, the same dynamics that produced the disruption in the first place, work to restore something closer to equilibrium, even if imperfectly, even if the return to baseline is gradual and uneven rather than immediate and complete. That is the historical pattern. That is what decades of observational data have established as the expected behavior following a stratospheric disruption of this kind. That is what the record would predict for a season involving even one significant sudden stratospheric warming event, let alone 3. That reset did not happen after the first event this season. The January disruption propagated downward, the surface patterns shifted toward blocked and amplified configurations, and the expected relaxation back toward zonal flow did not materialize within the time frame that historical precedent would suggest. The blocking highs that established themselves on the warm side of the circulation held their positions rather than being swept eastward. The cold trough that anchored the cold side of the dipole persisted rather than filling and moving on. The jet stream remained in its amplified meridional state, rather than straightening and accelerating back toward the faster, more organized flow that redistributes energy and prevents extremes from compounding. The atmosphere reached for its reset and did not find it. And then the February event arrived, landing on a system that had not reset, adding new stratospheric forcing to a troposphere still expressing the unresolved consequences of the January disruption. The reset that had not happened after the first event became even less likely after the second, because the new forcing reinforced the existing pattern, rather than disrupting it in a direction that might have allowed recovery. The heat ridge stayed warm, the cold trough stayed cold. The blocking highs that should have been dismantled by the returning zonal flow instead received new support from the altered stratospheric circulation above them. And when March arrived with the third event, the most structurally significant, the one with the documented wind reversals and the split vortex, the pattern that had been reinforced twice without reset was reinforced a third time. As of March of 2026, after 3 stratospheric disruptions across 3 consecutive months, the reset had not happened. The jet stream had not returned toward zonal flow. The dipole had not dissolved. The extremes had not moderated. If anything, they had intensified, the simultaneous records at both ends of the thermal spectrum suggesting a system that was not recovering toward equilibrium, but moving further from it. The question that this behavior forces is one that the standard framework for understanding post-SSW atmospheric recovery does not have a ready answer for. Why did the reset fail? Not once, which could be attributed to the particular character of that event or the particular state of the atmosphere when it arrived. Not twice, which could still be interpreted as an unusual but not impossible coincidence of circumstances. 3 times. 3 consecutive disruptions, each one finding a surface pattern that the previous disruption had established, each one reinforcing that pattern rather than washing it out. Something prevented the normal recovery mechanism from operating. Something kept the system locked in the state the disruptions had driven it into, rather than allowing the internal dynamics that normally restore circulation to do their work. Identifying what that something is turns out to be one of the more genuinely difficult questions in current atmospheric science. There is a concept that some researchers invoke to describe this kind of behavior, and it is worth examining carefully because it sits at the boundary between established science and active speculation, which is exactly where the most interesting and most important scientific questions tend to live. The concept is atmospheric resonance, and the basic idea is this. Under certain conditions, the wave patterns that develop in the atmosphere can feed back into themselves. The shape of a wave, the specific configuration of ridges and troughs in the jet stream, can influence the atmospheric flow in a way that reinforces and maintains that same wave shape, rather than allowing the normal processes of wave propagation and dissipation to evolve the pattern into something different. When this kind of resonance establishes, the pattern does not simply persist in the passive sense of not yet having been dismantled. It actively maintains itself. The wave recruits energy from the flow that would normally carry it away. The blocking high that should be swept eastward instead deflects the flow around itself in a way that sustains its own pressure gradient. The system that would normally unlock the pattern is operating within the pattern, following the path the pattern dictates rather than imposing an external correction. The physical basis for atmospheric resonance is not invented or fringe. There is a body of theoretical and observational work in the literature exploring conditions under which planetary-scale wave patterns can become quasi-stationary and self-reinforcing, and the mechanisms proposed, including interactions between the large-scale flow and the orographic forcing of mountain ranges, and resonance between the natural frequencies of atmospheric wave modes and the external forcing driving them, are physically coherent and have been explored in peer-reviewed research. What is not settled is whether these mechanisms are strong enough and common enough to account for the kind of sustained pattern locking we observed this season, and whether the specific conditions of 2025 into 2026 meet the criteria that the theoretical framework requires. The scientific literature on atmospheric resonance is active, contested, and unresolved in the ways that matter most for interpreting current events. Researchers who work on this topic are careful to distinguish between behavior that is consistent with resonance and behavior that has been demonstrated to result from resonance, and that distinction, in this case, has not yet been definitively resolved. What is observable, what does not require resolution of the theoretical debate, is the behavior itself. 3 stratospheric disruptions arrived in sequence across January, February, and March. Rather than alternating with recovery periods that allowed the surface circulation to return toward baseline between events, they compounded. Each reinforced the pattern the previous one had established. The surface expression of that compounding, the locked dipole, the amplified meridional jet stream, the simultaneous records at both ends of the thermal spectrum, held with a stability and persistence that the historical record for post-SSW surface responses does not readily explain. Whatever mechanism or combination of mechanisms produced that persistence, the persistence itself is documented. The data is not ambiguous on the behavioral level, even if it remains ambiguous on the mechanistic one. What is unknown? And this is the question that sits underneath everything else, and makes atmospheric scientists genuinely uncomfortable when they are being honest about the limits of current understanding, is whether this kind of pattern locking is becoming more frequent, or whether 2025 into 2026 represents an extreme outlier within a range of variability that the climate system has always contained. The observational record for stratospheric events and their surface consequences is measured in decades, not centuries. The satellite era, which provides the data quality required to characterize these events with confidence, extends back only to the 1970s. Within that roughly 50-year window, the number of seasons involving multiple stacked sudden stratospheric warming events is small enough that distinguishing between a genuine increase in frequency and natural clustering within a stationary distribution is statistically very difficult. The data required to answer the question with confidence does not yet exist in sufficient quantity. The record is too short. The events are too rare within that record to support strong conclusions about whether their frequency is changing. That uncertainty is not a reason to dismiss what happened this season, and it would be a mistake to treat it as one. Uncertainty about whether a pattern is becoming more common is not the same as evidence that it is not. The physical mechanisms that would drive increased frequency, Arctic amplification reducing the temperature gradient that powers the jet stream, a weaker jet stream more susceptible to the kind of wave amplification that produces and sustains blocking patterns, a more disrupted polar vortex responding to altered wave forcing from below, are documented processes operating in the observed direction. The question is not whether those mechanisms exist, it is whether they are yet strong enough and consistent enough to be producing a detectable change in the frequency of events like this season's. And the honest answer is that the observational record is not yet long enough to say, with the statistical confidence that science requires before drawing firm conclusions. What it is long enough to say is this: The atmosphere this season did something that the historical record suggests should be rare. It stacked 3 stratospheric disruptions without adequate recovery between them. It produced a surface pattern that locked rather than reset, that held simultaneous records at both ends of the thermal spectrum, that expressed the compounded consequence of months of stratospheric forcing in a single dramatic week of weather that broke records across multiple continents simultaneously. Whether that is the new normal or an extreme excursion from a stable baseline, the global consequences did not wait for the scientific community to resolve the question. They arrived in March of 2026. They are still arriving. And the atmosphere, characteristically indifferent to the debates we're having about it, continues doing what it has always done, redistributing energy, expressing imbalance, and occasionally reminding us, in the most unambiguous terms available to a planetary system, that the machinery we depend on is more complex and more fragile than our daily experience of it suggests. Part 9. Global Signals. Juneau, Alaska does not typically make international headlines. It is a small city of roughly 33,000 people, accessible primarily by boat or plane, tucked against mountains on the Alaska Panhandle in a geography that makes it one of the more logistically unusual state capitals in the United States. There are no roads connecting it to the rest of the North American highway system. If you want to leave Juneau by land, you cannot. You take a ferry or you fly, and in winter, when the weather closes in and the mountains disappear into cloud, sometimes you wait. The city exists in a kind of deliberate isolation that shapes everything about how it functions, its supply chains, its emergency response capacity, its infrastructure design. And it receives a lot of snow, more than almost any city in the United States, in fact. Snow is not news in Juneau. Snow is the background condition of winter, the expected state of affairs, the thing the city has spent decades building its operations around. Juneau knows snow the way a fishing town knows rain. It is simply the environment, which is precisely why 201.2 inches of seasonal snowfall, standing at roughly 230% of the city's seasonal average, is not a Juneau winter in any sense that the city's history or infrastructure was prepared for. 230% is not a heavy season. It is not a memorable season that old-timers will reference for the next decade. It is a number so far outside the range of what the city has experienced in its recorded history that the comparison to normal almost loses meaning. Normal is roughly 87 inches. 201 inches is more than double that, with enough margin remaining to constitute a full additional normal season on top of the doubled one. Emergency declarations were filed. Roofs collapsed under accumulated weight that the buildings were never engineered to support, because they were engineered for Juneau winters, not for whatever this was. Infrastructure designed around the assumption that snow would arrive in quantities the city knew how to manage found itself overwhelmed by quantities it had no framework for. The weight of the accumulation was, in the most literal physical sense, more than the built environment could bear. And the mechanism that produced it is not mysterious or isolated or specific to Juneau's local geography, although Juneau's geography certainly amplified the effect. The same persistent cold trough that has been holding temperatures 6 to 10 degrees below normal across Alaska and Canada for weeks, the cold side of the locked dipole we have been tracking throughout this discussion, positioned itself in a way that continuously funneled Arctic air into the region, while simultaneously allowing moisture from the relatively warm Gulf of Alaska to flow inland and interact with that cold air mass. Cold air and abundant moisture, sustained by a pattern that refused to move because the jet stream was too amplified and too slow to sweep it away, produced snowfall not as an event but as a condition. It snowed, and then it kept snowing. And the pattern that was producing the snow did not break down after a week the way a normal storm system would, because it was not a normal storm system. It was a locked atmospheric pattern expressing itself continuously at a geographic point that happened to be positioned directly in the pathway of maximum cold air delivery and maximum moisture availability simultaneously. The cold air pooled, the moisture was available, the pattern held, and the result was an accumulation that broke every historical record the city held, not by a narrow margin that might be attributed to natural variability and measurement uncertainty, but by a margin so large that it reclassifies what Juneau winters are capable of producing. This was not isolated weather behaving strangely in a remote corner of Alaska. This was the same mechanism, the same locked pattern, the same fractured jet stream expressing itself at a different geographic point on the same cold side of the same atmospheric fracture that was simultaneously producing record cold in Antarctica and record heat in the American Southwest. Across the Atlantic Ocean, the story repeated itself in a different language but with the same underlying grammar. The jet stream amplification that locked patterns over North America did not stop at the coastline. Rossby waves are planetary scale features. They operate at the scale of entire hemispheres, and the wave pattern that was holding the North American dipole in place was embedded in a larger hemispheric circulation that also influenced the flow over Europe. A stalled weather system, held in place by the same blocking structure that was anchoring the cold trough over Canada and Alaska, positioned itself over the central Atlantic in a way that directed a continuous flow of moist Atlantic air toward the European Alps. Under normal conditions, under a jet stream with enough speed and organisation to progress weather systems eastward, that flow would have been transient. The system would have moved, the moisture feed would have shifted, and the Alps would have received a significant but bounded snowfall event before the pattern evolved into something else. Under the conditions of late winter 2026, with the jet stream slow and the blocking structure resistant to the normal eastward progression, the system did not move. It sat, and it kept delivering moist Atlantic air against the alpine terrain for long enough to produce something that local records had no precedent for. Macunaga is a village of roughly 600 permanent residents sitting at the foot of Monte Rosa in the Italian Alps, at an elevation where significant snowfall is a routine feature of winter. It is not a place that surprises easily when it comes to mountain weather. 1.47 metres of snow in 24 hours, 4 feet and 10 inches of accumulation in a single day, surprised it. The mechanism involved what meteorologists call orographic amplification, the forced lifting of air against terrain. When moist Atlantic air moving inland encounters the vertical barrier of the Alpine Massif, it has nowhere to go but up. As it rises, it cools. As it cools, the moisture it carries condenses and falls as precipitation. The steeper and higher the terrain, the more rapid and complete that lifting process is, and the Alps, rising abruptly from the Po Valley to elevations above 4,000 metres, are among the most effective orographic lifting mechanisms in the world. Under normal circumstances, that effectiveness is bounded by the duration of the moisture feed, which is in turn bounded by how long a given weather system remains positioned to deliver Atlantic moisture to the alpine slopes before the jet stream carries it away. In late winter of 2026, that duration was not bounded in the normal way. The system stalled, the moisture feed continued, and the orographic amplification, operating at full efficiency for an extended period, produced snowfall rates that overwhelmed every response capacity in the region: avalanche mitigation, road clearing, emergency services, all of it outpaced by accumulation rates that the regional infrastructure had not been designed to handle, because nothing in the regional historical record suggested they needed to be. This was not a European weather event that happened to be unusual. This was the hemispheric reach of the same jet stream pattern expressing itself at a different longitude, through a different local mechanism, with different surface consequences but with the same underlying atmospheric cause. The fracture was not regional. It was not even continental. It spanned an ocean and expressed itself on 2 continents simultaneously, because the wave pattern that produced it operated at the scale of the entire hemisphere. And on the warm side of the dipole, separated from the snowfall records by the same atmospheric boundary that was spawning severe weather across the Midwest, the consequences were moving in an entirely different and equally extreme direction. 22 red flag warnings were issued across the United States in a single operational period, a simultaneous declaration of critical fire weather conditions across a geographic area larger than most countries on Earth. Red flag warnings are not routine cautionary notices. They represent a specific threshold combination of low humidity, high winds, and critically dry fuel conditions that fire weather meteorologists have determined creates conditions under which fire ignition is likely and fire spread, once ignition occurs, can become rapid and uncontrollable. 22 of them, simultaneously, across a swath of the country stretching from the southwest through the southern plains, represents a fire weather situation of a scale and geographic extent that is rare even in years when drought conditions have been building for months. Relative humidity readings of 4 to 6% were recorded across parts of the southwest and southern plains. 4 to 6%. The threshold at which wood is considered critically dry for fire behaviour purposes is generally around 10%. At 4 to 6%, vegetation that would normally have some resistance to ignition becomes essentially indistinguishable from cured fuel. Grasses, shrubs, and the understory of woodlands reach moisture contents low enough that a single ignition source, a downed power line, a vehicle spark, a discarded cigarette, can initiate a fire that spreads faster than suppression resources can respond to it. Energy release component values, the index fire weather meteorologists use to assess the energy available in the fuel bed for combustion, were at or near their maximum recorded levels across the affected region. These are not elevated conditions. These are the conditions that produce the fires that make the news, that consume structures by the hundreds, that force mass evacuations, that burn at intensities that defy conventional suppression. The heat ridge producing these conditions was not simply warming the air above the affected region. It was systematically removing moisture from every surface it touched, pulling water from soil, from vegetation, from the air itself, in a sustained desiccation process that had been operating for weeks under the locked pattern. The same blocking high that was holding temperatures 6 to 10 degrees above normal was also suppressing cloud formation, maximizing solar radiation reaching the surface, and driving the persistent downslope winds that accelerate evaporation and carry fire once it starts. And the same pressure gradient that was fueling the Midwest storm system was generating strong surface winds across the fire weather zone, winds that, in the presence of critically dry fuels and low humidity, transform a fire weather situation from serious to catastrophic. This is what the warm side of a locked dipole looks like at the surface, rendered not in temperature records or snowfall totals but in the colour of the sky when the smoke arrives, and the speed at which a normal afternoon becomes an emergency. It is the direct surface expression of the same atmospheric fracture that was simultaneously burying Macunaga under 5 feet of snow, collapsing roofs in Juneau under the weight of a double winter, and building the rotation that would release as tornadoes across the Midwest after dark. One fracture, one pattern, one week, every extreme a different face of the same broken machinery. Part 10. Controversy and Unknowns. There is something worth noting about how the March 2026 records were covered in the media, and it requires a degree of honesty that science communication does not always afford itself. Coverage choices are not neutral. They are not simply the product of what happened and how dramatic it was. They reflect editorial judgments about what fits existing narratives, what audiences will find intuitive, and what requires the least amount of explanatory scaffolding to communicate quickly and compellingly. Those judgments are understandable. Media operates under real constraints of time, attention, and audience comprehension, but they have consequences for how the public understands the atmosphere, and those consequences were visible in March of 2026 in ways that are worth examining directly. When Antarctica recorded an anomalous warming event in 2020, temperatures surging nearly 40 degrees Celsius above normal across parts of the continent, a genuinely extraordinary departure from any precedent in the observational record, it received widespread international attention. Major publications ran it as a leading story. Graphics showed the temperature anomaly in vivid colour. Scientists were quoted at length explaining what it meant and why it mattered. The event was framed as a signal, a demonstration of how dramatically and how rapidly conditions could depart from expectations, a warning embedded in data about the trajectory of a changing climate system. That framing was appropriate. The event warranted exactly the attention it received. A 40 degrees Celsius anomaly above normal in one of the most isolated and stable atmospheric environments on Earth is a remarkable thing, and treating it as remarkable was the correct response. The minus 105.5 degree Fahrenheit reading at Vostok Station in March of 2026 received substantially less coverage. Not zero coverage, the record was reported in meteorological and science-focused outlets, noted in weather tracking communities, mentioned in passing in broader climate coverage. But the volume, prominence, and analytical depth of that coverage was not comparable to what the 2020 warming event received, despite the fact that the Vostok cold record represents a departure from normal that is, in percentage terms and in the context of what the station has historically recorded for that month, equally extraordinary. A record low in the same region, in the same category of extreme departure from seasonal expectations, covered at a fraction of the intensity. The asymmetry is measurable, it is not subtle. The reasons for that asymmetry are worth understanding rather than simply criticizing, because some of them are legitimate and some of them are not, and distinguishing between the two matters for how we think about improving science communication going forward. Cold records are genuinely harder to explain in the context of the dominant narrative framework through which climate change is publicly understood. That framework, warming planet, rising temperatures, more heat, is accurate as a description of the long-term global trend, but it creates an explanatory friction when confronted with a record cold event that the framework does not immediately accommodate. An editor considering whether to run a major story on the coldest March temperature ever recorded at Vostok faces a real communication challenge. How do you explain to a general audience why a record cold event is consistent with, and in some ways produced by, the same processes driving long-term warming? That explanation requires introducing the polar vortex, stratospheric warming events, jet stream amplification, and atmospheric dipoles, concepts that take time and care to communicate accurately and that resist the kind of simple, immediate framing that makes a story shareable and accessible. The warming event in 2020 was easier. Temperatures went up dramatically in a place that is supposed to be cold. The narrative wrote itself, but easier to communicate is not the same as more important to communicate, and when coverage choices systematically emphasize one category of extreme, anomalous warmth, while underemphasizing another anomalous cold, the public ends up with a partial and distorted picture of what the atmosphere is actually doing. Not a false picture exactly, because the warmth events that receive coverage are real and significant, but an incomplete one, because the cold events that receive less coverage are equally real, equally significant, and, crucially, produced by the same mechanism as the warm events. They are not separate stories with separate causes. They are the two outputs of the same machine. Covering one and not the other is like reporting on a storm's rainfall while declining to mention the flooding it caused, on the grounds that rain is more intuitive and flooding requires additional explanation. The mechanism that produced the Vostok cold record in March of 2026, the stratospheric disruption, the fractured polar vortex, the locked jet stream, the amplified dipole, is the same mechanism that produced the 112 Fahrenheit reading in the American Southwest the same week. Climate change attribution research, including the rigorous and carefully bounded work produced by the World Weather Attribution Group, can link the heat side of this pattern to long-term warming trends with reasonable confidence. The elevated baseline temperatures that made the Southwest heat record possible reflect decades of accumulated warming that attribution science can quantify. That linkage is real and the research supporting it is robust. The cold event at Vostok is driven by different proximate physics, radiational cooling, stable temperature inversion, clear skies, the specific conditions that allow the Antarctic plateau to shed heat into space at an extraordinary rate, and those local physics do not carry the same direct attribution signal that the heat side carries. The cold record is not evidence of global cooling. It is evidence of a disrupted atmospheric circulation producing extreme conditions at both ends of the thermal spectrum simultaneously, with the cold end expressing itself through local physics that are sensitive to circulation changes even when those changes are ultimately connected to a warming-driven process. Both are real, both are extreme, both emerge from the same disrupted atmospheric state. The scientific and public challenge is to hold both in view at the same time, resisting the temptation to select for the data that fits the existing narrative and against the data that requires more explanation. The atmosphere does not select. It does not pick a side or adjust its behaviour to match the framework through which humans are currently interpreting it. It expresses the full consequence of whatever state it is in, and in March of 2026, the state it was in produced both the hottest and the coldest simultaneously from the same cause in the same week. The deeper question that sits underneath the coverage asymmetry, the question about whether the atmosphere is entering a new regime characterized by more frequent stratospheric disruptions, more persistent pattern locking, and more intense simultaneous extremes at both ends of the thermal spectrum, is genuinely unresolved in the scientific literature, and that lack of resolution deserves to be communicated honestly, rather than papered over with false confidence in either direction. The hypothesis that Arctic amplification is weakening the jet stream and increasing the frequency and persistence of blocking patterns and wave amplification has supporting evidence. The physical mechanism is coherent, the directional trend in the observational data is consistent with the prediction, and the events of the current season are consistent with what the hypothesis would lead you to expect. It also has serious critics within the atmospheric science community who argue that the statistical evidence for increased jet stream waviness is not yet robust enough to support confident conclusions, that the observational record is too short and too variable to distinguish a genuine trend from a cluster of anomalous events within a stationary distribution, and that attribution of specific events to jet stream changes remains methodologically contested. Both positions are held by serious researchers working with the same data and arriving at different conclusions through legitimate scientific disagreement. The honest summary of where the field stands is this: the signal is consistent with the direction the hypothesis predicts, but the signal is not yet strong enough relative to the noise of natural variability in a short observational record to support the conclusion that a new regime has been definitively established. What researchers can say is that what they are observing fits the pattern the hypothesis describes. What they cannot say, not yet, not with the confidence that the evidence currently supports, is whether that fit reflects a genuine causal relationship or a coincidence of timing within a range of variability the climate system has always produced. The honest answer is that we do not know. And in a system as genuinely complex as Earth's atmosphere, in a domain where overconfidence in either direction has costs to credibility, costs to policy, costs to public understanding, honest uncertainty is not a weakness to be apologized for. It is the most accurate thing that can be said, and accuracy is more valuable than the false comfort of a cleaner answer. One further layer deserves attention before we move on, not because it is confirmed, not because the evidence for it meets the standard that scientific conclusions require, but because it represents exactly the kind of question that responsible scientific curiosity should hold open rather than dismiss. Solar cycle 25, the current solar cycle, has been running significantly more active than forecasters initially predicted. Solar maximum conditions, the peak of the approximately 11-year cycle of solar magnetic activity, arrived earlier and with greater intensity than the models used to project it suggested they would. The Sun, in other words, has been doing more than expected during the same period in which the upper atmosphere has been doing less than normal in the sense of maintaining stable, organised circulation patterns. The upper atmosphere is known to respond to solar activity through several mechanisms, including variations in ultraviolet radiation that affect stratospheric ozone chemistry and temperature structure, and through energetic particle precipitation during geomagnetic storm events that can deposit energy directly into the upper stratosphere and mesosphere. The pathways by which these solar influences might propagate downward to affect the stratospheric circulation, and through it the behaviour of the polar vortex and the jet stream, are areas of active and ongoing research. They are not fringe science. They are legitimate open questions in a field that is still characterising the full range of external forcings that influence atmospheric behaviour. No confirmed causal link exists between the activity level of solar cycle 25 and the triple sudden stratospheric warming events of the 2025 into 2026 winter season. That must be stated clearly. The coincidence of timing, an unusually active sun during an unusually disrupted upper atmosphere, is not evidence of causation. Correlation at this level of temporal resolution with a single season's worth of events proves nothing. But the question of whether solar variability is contributing a modulating influence on stratospheric instability, adding a layer of external forcing on top of the internal dynamics already producing disruptions, is a question that the available evidence does not allow us to rule out. The sun has been unusually active. The upper atmosphere has been unusually disrupted. Whether those two facts are connected, and if so through what mechanism and with what magnitude of effect, is a question that researchers are actively working on, and that the current season has given them unusually rich material to work with. It is worth holding open, not as a conclusion, not as an explanation, but as a question, the kind of question that honest inquiry keeps visible rather than closing prematurely, because the history of atmospheric science is full of mechanisms that were dismissed as speculative before the data accumulated enough to take them seriously. Part 11. The system under stress. Everything we have covered, the 217-degree spread, the simultaneous records at both ends of the thermal spectrum, the triple stratospheric disruptions that stacked without recovery between them, the locked jet stream that refused to reset, the Midwest outbreak forming at the collision boundary, the snowfall records in Juneau and Macunaga, the fire weather crisis unfolding across the southwest and southern plains, all of it is a symptom. Every record, every warning, every emergency declaration, every roof that collapsed under the weight of accumulated snow, and every hillside that ignited under humidity readings below 5% symptoms. The temperature extremes are not the story. They are what the story looks like from the surface, rendered in numbers that humans can measure and report and react to. The actual story operates at a level beneath the thermometer readings, and the storm tracks and the snowfall totals. The actual story is about energy, specifically about what happens when the planetary system responsible for distributing energy evenly around the surface of the Earth loses the ability to do that job effectively, and what it looks like when that system attempts violently and imperfectly to correct itself. The atmosphere exists to move heat. That is its primary function, stated as simply as the physics allow. Energy from the sun does not arrive at the Earth's surface uniformly. It arrives concentrated at the equator and the tropics, where the geometry of the planet means that sunlight strikes at a more direct angle and delivers more energy per unit of surface area than it does at higher latitudes. The equatorial regions receive far more solar energy than they can absorb and radiate away without becoming uninhabitable, without temperatures climbing to levels that would make complex biochemistry impossible. The polar regions receive far less than they would need to maintain temperatures anywhere near the range that supports liquid water and the processes that depend on it. The atmosphere's job, the job it has been doing in one form or another for hundreds of millions of years, is to take the excess energy from the places where it accumulates and move it toward the places where it is deficient. To act as a planetary heat distribution system, constantly in motion, constantly transferring warmth from the equator toward the poles, moderating temperatures across the entire surface, and maintaining the conditions that make the kind of life we are familiar with possible. It does this through circulation, the jet streams that circle the hemispheres at high altitudes, the ocean currents that carry warm water poleward and cold water equatorward in a global conveyor that operates on timescales ranging from seasons to centuries, the storm systems that form along temperature boundaries and transport enormous quantities of energy in the form of latent heat released when water vapor condenses into precipitation, the global patterns of wind and pressure that have shaped weather on Earth across geological time. When that circulation is functioning within its normal range, when the jet stream is moving efficiently, when blocking patterns are transient rather than persistent, when the polar vortex is containing Arctic air rather than releasing it, the energy is distributed broadly enough across the surface that no single region accumulates a catastrophic excess or deficit. Extremes exist within a functioning circulation. Cold outbreaks happen, heat waves develop. Severe weather outbreaks occur at the boundaries between air masses, but those extremes are bounded by the efficiency of the redistribution system. Energy moves before it accumulates to the point of producing records that have no historical precedent. The system self-corrects before the imbalance grows large enough to generate simultaneous records at both ends of the thermal spectrum in the same week. The correction mechanism is built into the circulation itself. The same jet stream that allows extremes to develop also eventually sweeps them away and restores something closer to balance. What a dipole of the kind we observed in March of 2026 represents, understood in this framing, is a failure of distribution. Not a complete failure. The atmosphere never stops moving entirely, never stops transferring energy from equator toward poles through every mechanism available to it, but a significant, sustained, compounding failure of the efficiency of that distribution, producing consequences at the surface that accumulate in direct proportion to how long the failure persists. Energy is accumulating on the warm side of the dipole because the locked amplified jet stream is not moving it northward with the efficiency that a more zonal, faster circulation would provide. The heat ridge sits over the western United States, holding temperatures 6 to 10 degrees above normal for weeks, because the circulation that should be sweeping that excess warmth poleward has slowed and stalled. Cold is deepening on the cold side because Arctic air that the polar vortex was supposed to contain has been displaced southward by the stratospheric disruptions and is now pooling over Canada and Alaska and the northern plains, held in place by the same locked pattern that is trapping the warmth on the other side. The temperature extremes are not random events generated by unrelated processes. They are the surface expression of a single, organised atmospheric imbalance, an imbalance that the circulation is both creating through its degraded state and failing to resolve because its degraded state prevents the normal correction mechanisms from operating effectively. And here is the physical insight that matters most for understanding what comes next, and why the boundary between the two sides of the dipole is the most dangerous place on the surface during an event of this kind. The larger the imbalance, the more violent the correction when it finally arrives. The atmosphere does not forgive stored energy. It does not allow excess warmth to simply dissipate gently into space or permit displaced cold to gradually moderate back toward normal without consequence. It collects the energy that the degraded circulation has failed to distribute, holds it in the regions where it has accumulated, allows the imbalance between those regions to grow, and then releases it, all of it, or as much as the dynamics allow in a given event at the boundary between the two sides, in the form of the most powerful storm systems the mid-latitudes are capable of producing. The Midwest outbreak forming at the collision boundary between the record heat and the record cold is not an incidental feature of this atmospheric configuration. It is the correction mechanism. It is the atmosphere doing, violently and locally, what it has been failing to do efficiently and broadly for weeks. The supercells and the tornadoes and the pneumonia front are not separate from the dipole. They are the dipole releasing. Modelling what happens if this pattern, stacked stratospheric disruptions without adequate recovery between them, locked dipoles holding simultaneous extremes for weeks, meridional, jet stream behaviour that prevents efficient energy redistribution, becomes more frequent is an exercise the atmospheric science community is actively engaged in, and the results of that modelling exercise are not reassuring in any of the scenarios that current understanding makes plausible. More frequent pattern locking means more persistent extremes on both sides simultaneously, not alternating heat waves and cold outbreaks in a sequence that allows some recovery, but heat and cold coexisting in adjacent regions for extended periods, each deepening while the other deepens, each making the eventual correction more violent. It means more frequent and more severe weather outbreaks at the boundary zones where the two sides are eventually forced into contact, more events like the Midwest outbreak, with more energy available for release because the imbalance has had more time to accumulate before the correction arrives. It means more red flag warning days on the warm side and more catastrophic snowfall events on the cold side occurring in the same season, driven by the same mechanism, stressing response systems that were designed for a world where those extremes occurred in different years rather than different weeks. And it means compound events, the scenario that emergency management and public health systems are least prepared for, where a region that has already been stressed and depleted by one extreme is then struck by another before meaningful recovery has occurred, becoming not the rare exception that planning documents treat them as, but the expected pattern that resource allocation and infrastructure design need to account for. The honest uncertainty is real, and it deserves to be stated without minimization. This could be an extreme outlier, a coincidence of atmospheric conditions so improbable that it falls at the far tail of natural variability without representing any change in the underlying behavior of the system. The observational record for events of this kind is short. The models used to project future behavior are imperfect in ways that matter for the specific questions being asked. The system is genuinely complex in ways that resist confident prediction, even with the best available tools and the most careful analysis. All of that is true, and none of it should be papered over in the interest of a cleaner narrative. But the uncertainty cuts both ways with equal force, and that symmetry matters. The same limited observational record that prevents us from confirming with statistical confidence that a new regime has established itself also prevents us from ruling one out. The same model imperfections that limit our ability to project future event frequency with precision also limit our ability to confidently assign the current season to natural variability. The physical mechanism, reduced Arctic to mid-latitude temperature gradient, weaker jet stream, more persistent wave amplification, is not a hypothesis waiting for observational support. It is an observed process operating in the observed direction. Whether the signal is strong enough to constitute a detectable trend against the background of natural variability is a statistical question that the current record cannot definitively resolve. Whether it is strong enough to take seriously as a possibility that warrants attention and preparation is a different question entirely, with a different answer. We began this with two numbers, minus 105.5 degrees Fahrenheit at Vostok Station, Antarctica, 112 degrees Fahrenheit in the United States, in the same week, on the same planet, produced by the same disrupted atmospheric circulation, a circulation fractured by three stacked stratospheric events that arrived faster than the system could absorb and recover from them, that locked into a dipole pattern holding both extremes simultaneously for weeks, that expressed itself in snowfall records and fire weather crises and severe weather outbreaks across multiple continents, and that was releasing its accumulated stored energy in real time across the American Midwest as the cold side and the warm side were finally forced into contact along the boundary that had been building between them. These were not coincidences. They were not separate weather stories that happened to occur in the same calendar week. They were different surface expressions of a single coherent atmospheric state, a state the system arrived at through a cascade of stratospheric disruptions, and that it will maintain until it has expended enough stored energy to return towards something closer to balance. For 1 week in March of 2026, the atmosphere showed us, with a clarity that the instrument record will preserve long after the storms have passed and the temperatures have moderated, what it looks like when the distribution system breaks down, and how violently and how globally and how simultaneously it tries to restore what it has lost. The question that the data does not yet answer, and that the atmosphere itself is still in the process of resolving, is whether what we witnessed was the system at the outer edge of what natural variability can produce, or whether it was the atmosphere at the beginning of something, showing us not its limit, but its new direction.